Welcome to Chapter 1, Overview of Computers and Programming Languages. By the end of this chapter, you'll understand the components of a computer system, be able to develop simple program logic using pseudocode and flowcharts, recognize the program development cycle, and understand programming environments and how programming models have evolved. Computer systems combine hardware and software. Hardware is tangible. The CPU handles calculations, RAM provides volatile memory, SSDs and HDDs give permanent storage, plus input devices like the keyboard, output devices like the monitor, the motherboard connecting everything, and the power supply. Software is intangible. System software like the OS kernel, antivirus, and file explorer. Application software like Word, Excel, or Chrome, and programming IDEs like VS Code, compilers, and interpreters. Here's how hardware and software work together. The programmer writes code, which becomes instructions the CPU executes. Memory temporarily stores those instructions and data while the program runs. Input devices feed data in, output devices display results, and storage devices hold the software itself. The operating system sits in the middle, bridging communication between hardware and software so everything works together seamlessly. Storage splits into two categories. Volatile storage loses its information when power is lost. That's short-term storage like RAM and CPU cache, L1, L2, L3, used for whatever the system is actively working on. Non-volatile storage retains information even without power. That's long-term storage like SSDs, HDDs, and flash drives, used for anything you need to keep. Every properly structured program follows the same sequence: input, processing, output. Input is the information fed into the program, from a keyboard, storage, or another input device. Processing executes the program's instructions on that input, done by the CPU, organizing and calculating. Output sends the results to a device, like a screen, and may also be stored for later retrieval. Here's the same simple program, Hello World, written in 3 different languages, C++, Java, and Python. Notice how differently each one structures the same basic instruction. That's syntax, the grammatical rules of a programming language, dictating exactly how code must be written for that language to understand it. Syntax errors are mistakes in code structure or grammar, a missing semicolon, a misspelled word, improper indentation, caught during compilation or interpretation, and they prevent the program from running at all. Logical errors are mistakes in the program's logic itself, an incorrect formula, the wrong condition in a loop, caught only at runtime, since the program still runs, just with the wrong output. The program development cycle has 7 steps. Understand the problem, defining inputs and outputs, plan the logic using flowcharts, pseudocode, or algorithms, code the program in a suitable language, translate it to machine language by compiling or interpreting, test the program, debugging until it's correct, deploy it for users, and maintain it, updating and fixing issues as they come up. Input, processing, output, in more detail. Input accepts data into the program through variable declaration and initialization, kicking off the program's flow. Processing performs calculations on that input, executing the program's logic to convert it into meaningful results. Output displays those results to the user, transmits them to a file or device, and may save the processed data for later. Here's input processing output as an actual Python program. It takes a number from the user as input, doubles it during processing, and prints the result as output. Notice how the comments mark exactly which part of the code handles each of the 3 steps. Here's that same doubling program written in C++. Same 3 steps, same logic, different syntax. Syn reads the input, the processing line doubles the number, and count prints the output. Comparing this to the Python version is a good way to see how the underlying logic stays identical, even as the language changes. And here's the same program again in Java, using a scanner object to read input instead of Syn or Python's input function. The processing and output steps follow the same pattern as the other 2 languages. This is the core idea of input, processing, output showing up identically across 3 completely different syntaxes. Understanding the problem is step 1 of the development cycle. Define the user requirements by identifying what the program needs to achieve and gathering input from stakeholders. Clarify the objectives, the expected output, plus any constraints. Analyze the input requirements to make sure the data you'll receive is sufficient and accurate. And document the problem with written descriptions and diagrams to visualize it. Planning the logic is step 2. Design algorithms by breaking the problem into smaller steps and outlining the sequence of operations. Use flowcharts to diagram the program's flow, including decision points and loops. Write pseudocode, plain English describing the logic, focused on input, processing, and output. And consider edge cases, unusual or extreme scenarios, and how the program should handle them. Desk checking is a manual process where you simulate a program's execution on paper before ever running it to verify the logic is correct. Here, with my number set to 5, we trace through each step: start, Then input sets my number to 5. Processing calculates my answer as 5 times 2, giving 10, and output displays that 10. Since the traced result matches what we'd expect, the logic checks out before the program is ever actually executed. Coding the program is step 3. Choose a programming language suited to the task and its requirements. Follow coding standards. Consistent indentation, clear naming, clean and readable code. Translate your logic into actual code, implementing the flowcharts or pseudocode you planned earlier. And comment and document as you go, explaining complex sections for your future self or other developers. A compiler translates the entire program into machine code before execution, producing a file like in .exe. Errors are caught at compile time, and since it's pre-translated, it runs faster. C++ and Java are compiled. An interpreter translates and runs code line by line during execution, directly from the source code. Errors only show up at runtime, and it's slower since there's no pre-compiled file. Python, JavaScript, and PHP are interpreted. Testing the program is step 5. Identify test cases. Input scenarios covering normal, edge, and invalid cases. Run the program with those prepared cases, and observe how it handles each one. Debug any errors you find, whether syntax or logic, and rerun tests after every fix. And validate the results by comparing actual output against what you expected, confirming the program meets its requirements. Deploying the program is step 6. Prepare the deployment environment, making sure hardware and software requirements are met and the production environment is configured correctly. Install the program and set up any dependencies it needs. Conduct final testing in that live environment, verifying performance, security, and functionality. And train users, providing documentation and support during their first experience with it. Maintaining the program is step 7, and it never really stops. Monitor performance, tracking errors, and collecting user feedback. Fix bugs as they're discovered, testing every fix carefully so it doesn't introduce new problems. Enhance features based on what users actually need, and optimize existing ones. And update for compatibility, keeping pace with new hardware, software, and dependencies over time. Pseudocode is a simple, plain English representation of a program's steps, focused purely on logic, highlighting input, processing, and output clearly, and easy to translate into any programming language. Flowcharts are the visual counterpart, using symbols to depict the program's flow, including decision points and loops, easy for other programmers, or even non-programmers, to follow and understand the structure. Here's the same simple double and number program shown 3 ways. As a flowchart, tracing input, processing and output visually with start and end points. As pseudocode, describing those same steps in plain English. And as actual Python code implementing that exact logic. This progression, pseudocode, to flowchart to source code, is exactly how a program typically gets planned and built. Flowcharts use standard symbols with specific meanings. An oval marks the start or end of a process. A rectangle represents a process or operation step. An arrow shows the flow between steps. A diamond represents a decision or selection point, a yes or no conditional. And a parallelogram represents input and output operations. Programming environments come in a few types. Integrated development environments, like Visual Studio or Codespaces, bundle code editors, debuggers, and compilers into one comprehensive tool. Text editors, like VS Code, Sublime Text, or Notepad++, let you code manually, often with extensions added on. Graphical user interfaces, like MIT App Inventor or Scratch, let you program through drag and drop, ideal for beginners. And command line interfaces, using tools like PowerShell, Python, or Bash, let you program directly through terminal commands. Procedural programming focuses on functions and procedures, structured as a sequence of instructions with reusable functions and a linear, top-down flow, easier to trace step by step. C, Pascal, and Fortran are procedural languages. Object-oriented programming focuses on objects and classes instead. Objects have properties, which describe them, and methods, which are actions they can perform, with inheritance letting you create new objects based on existing ones. Java, Python, and C++ all support this style. Before next class, complete pseudocode and a flowchart for an everyday task of your choice. Cooking a recipe, your morning routine, fixing something around the house. Print both out and bring them to class for review. This is great practice translating a real process you already know into the structured logic we've covered throughout this chapter.